Hello! Today I'll be going over my preparation for Criterion A in science. And firstly, let's begin with waves. There are two types of waves. There are transverse waves and longitudinal waves. And transverse waves are waves that oscillate perpendicularly towards the direction they're going. So you might ask, what is perpendicular? Perpendicular simply means a right angle. It's the thing that forms a right angle. So let's start. So we have the rest position here, and we have the wave over here, and then to have the wave over here, which makes it like this wave altogether. As you can see here, it oscillates perpendicularly, assuming that this thing forms a right angle, of course. So let's continue. Uh, we also have the longitudinal waves. So the longitudinal waves could be illustrated in this way. So they continue and continue and continue, and assuming these get bunched up and then continue. Okay, this is not my proudest illustration, not my best illustration. However, you can see over here there is a over here is a compression over here and over here. These are they are compressed, and this is a refraction. So a refraction is the opposite of a compression. So they're like becoming rarer, as if they are moving away from each other. And uh, so a longitudinal wave is simply a wave which is which is moving in the same dimension. That's why you don't see any y-axis or z-axis and x-axis, which you could have seen in the uh, transverse waves. This is just 2D. Okay, now let's go over the electromagnetic waves. So, what is electromagnetic waves? It is waves that all do not need a medium to travel to, and they are all transverse waves. And also, what is a mechanical wave? It's a wave that passes through a medium, I'm pretty sure. And let's begin. So, we're going to start by illustrating a wave. A electromagnetic wave, as a matter of fact. To make the illustration simpler, we're going to do this, and like this over here, and yeah. Let's look at a transverse wave and label and describe it. Okay, so this is a rest illustration. So this line over here is the rest position. It's the areas where there is zero displacement. Then we have over here we have the crest, which is the highest point of the wave. And this point, let's assume it's also a crest. The lowest point of a wave is the fro. And now you might be wondering, what is displacement? Displacement is simply the amount it is from the rest position. So this is a displacement, this is displacement, but of course this is more displacement, and the amplitude is the most displacement from the amplitude. So the amplitude is the largest displacement you can get from the rest position. So now we have labeled these stuff. What's the wavelength? A wavelength is simply a full cycle, a full oscillation, and it can be described from two identical points in a wave, such as a crest to a crest. So we can do this, and then imagine this wavelength. This can be perfectly imagined because you can imagine for yourself that this wave starts here, goes down, goes up, and then you can fill it in again and again and again. So the period is the time taken for one full oscillation. So basically, from going to crest to a crest to happen, which is usually measured in seconds. And the frequency is how many oscillations from crest to crest or any other point to point can occur in a second. The velocity is the speed that a wave is traveling at in one dimension. So it's going for that, no, in one direction. Sorry, and for example, this direction. So, have you heard of formula triangles? They're actually quite useful. Formula triangles can help you understand how to organize formulas because they are very simple. They consist of three ideas and you can organize them by a triangle. So let's think about the wave equation. For a wave equation, let's simply begin by drawing the wave again. And we see it now. So the wave equation can describe the simplified one can describe three things in the wave: the frequency, the wavelength, or the velocity. And the frequency is in hertz. The velocity is in meters a second. And the wavelength is measured in meters in general. So these are the measurements that are going to be put through. So hertz for frequency, which is basically how many cycles in a second, meters a second in velocity, yeah, how many meters a second, and wavelength is the amount of meters. So we can describe, for example, the distance from this point to this point. We can describe how fast the wave is going, and we can also describe how many times this point goes to that point when it's moving for 1 second. Okay, so let's start with the triangle. And I'm going to illustrate it over here. Oh, I already messed up. Over here. So we have velocity. And then we have the wavelength, which is represented by like a Greek symbol called lambda. And then we have frequency, which is represented by the F. So, how a formula triangle works is basically you can split it. So, imagine that we are going to begin by finding the other. So we have two things and we have one unknown. Let's say we're going to try to find the velocity. So what you do is velocity equals to, as you see here, those are on the bottom, both next to each other. So then it becomes the frequency times the wavelength. And this can be expanded for something else. Let's say we want to find the frequency. What you do now is that you imagine that you remove frequency over here, and as you can see here, let's say we remove a little bit more, and magically it seems to be a division sign. So we have velocity, the frequency equals the velocity divided by the wavelength. So let's write it down. And for if we want to find the wavelength, let's just make this triangle real quick again. We have frequency, and then we arrange this, and it magically becomes the wavelength equals to the velocity frequency. Okay, so now we understand how to derive the formulas from a formula triangle. and we also understand how a formula triangle works. So let's see if we can use this formulas for ourselves. So let's start with writing them down again. So the velocity equals to the frequency times wavelength. The frequency equals to velocity divided by wavelength, and the wavelength equals to velocity divided by frequency. Frequency. Okay, so imagine a situation where we need to calculate the speed of a wavelength. So the v, let v be the velocity, okay, and we know both the frequency and the wavelength. So assuming that the frequency is 5 in terms of hertz, and the frequency is 5 in terms of hertz, and the wavelength is going to be let's say 4 meters. So what you do here is you just multiply. So v equals to 20, and you also need to remember what unit we're using for this. And as you see, for the velocity it's meters a second, so we do meters a second. Okay, so now looking at this, you might be thinking, why does this formula work? It's simply because, as you imagine, what is the wavelength? It's the position from one crest to one crest, and the frequency is how much some times the wave like cycles in 1 second, and because we are doing this in second, assuming this is 1 second, right? Then it means that we're really just calculating how long the distance of one wavelength is, and then multiplying it by how many times it happens to get the total length that's traveled in 1 second. Now let's be moving on to the frequency. So as let's say we have the frequency over here equals to, let's say we have the velocity of 7, just a random value again, 7 meters a second, and we have it divided by the wavelength. Let's say it's 5 meters. Okay, so I imagine this. We have to calculate it, and let's just do some maths over here. We have 7 divided by 5. This is 120.4. So now the frequency equals to 1.4. And what do we write frequency in? We write it in hertz. Yes. Okay. So how does this thing work? How do you think that we can calculate the frequency that something happens? So firstly, we know the wavelength, right? It's the crest to crest, and we also know how many times how quickly it happens. So the only thing you need to know now is how the speed is related to speed divided by the wavelength is related to the frequency. And because the frequency is how many cycles happen in a second, if you divide it by the actual length of the wave, you get the actual number of a full cycle. So let's say this was actually 5 meters. If you divide it by 5, then you get 1 for 1 cycle, right? Then that works. And now let's discuss the last part of this formula, the what's it called again? The wavelength. This symbol does not look that well. uh, equals to, let's say with our velocity is, I don't know, feeling like 1, okay? 1 meters a second, and divided by the frequency of 0.5 hertz. Where is it? Okay, so what we do here is obviously we just calculate it, equals to 2, and because the wavelength is written in meters, we write meters. So how does this work? Okay, so basically you have 1 meter in a second, which is the unit, and then you have the hertz, which measures the cycles. So if you divide the amount of cycles that happen in that amount of time, and they have the same time frame of 1 second, then you will find out the wavelength. And this is it for uh, the electromagnetic waves. We will later be discussing further into electromagnetic waves. Hello back. So now we're going to discuss the electromagnetic spectrum and the components inside of it. So firstly, going back to recap, what is an electromagnetic wave? Let's draw a small illustration over here. So an electromagnetic wave is a wave that is transverse, which means that it when it moves, it oscillates perpendicularly. So this is a right angle, and it also has an electric field and a magnetic field that's acting as forces on it. This does not mean that one side is electric and one side is magnetic. They are both together, working together. And another cool thing is that electromagnetic waves can travel through a vacuum, which also is no medium, because a vacuum is, I'm pretty sure the meaning is the state of having nothing. Practically nothing, no matter. Okay, so let's begin. I assume you draw a line over here. Okay, mimicking this way. Okay, so we have the high. Oh yeah, low frequency, high frequency. So again, a low frequency simply means that the wave gets from crest to crest or full cycle less, and for 1 second usually, what's used to measure. High frequency is that the wave like goes complete cycles in a higher rate. So in the low frequency areas, we start with radio waves. Then we move on to microwaves. And maybe to make it more exciting, I could use another color now. Now infrared rays. And then we have visible light. And then maybe we can swap another color to make it more interesting. We have ultraviolet, ultraviolet light. And then maybe we can extend it further to make it possible to read more. X-rays. And then we have gamma ray. Okay. So we have low frequency and high frequency. So let's think of some stuff that can be used for all of each one of them. So starting at the lower frequencies, we have the radio waves. Radio waves can be used for radio signals. It can be also used for Wi-Fi signals. And moving on to microwaves, it's the obvious one. It can be used for microwaves using the radiation to warm up food. And infrared waves, it can be used to, for example, for heat cameras to see for whether there's a person in the forest which is cold and identifying them. Visible light can be used to identifying colors, as obviously, because all of the colors in the visible light are colors that we can see, as obviously, and it can be used for cameras too. And ultraviolet light, it can, for example, be used to ready food. For example, for pasteurizing milk, because milk itself, in the raw form, is dangerous and it has the bacteria. But once you pasteurize it with UV light by practically warming it up and killing the bacteria, then it becomes safe to drink. X-rays. There's a medicinal use where we can look through the skin and examine people's skeletons and bones, because it is good at that. And gamma rays, it can be used for killing tumors, but it can also create tumors. And what we need to know is that the low frequency, as mentioned previously, means that a wave has completed less cycles in a given unit of time, such as 1 second. And high frequency means that it completes more cycles in a given unit of time, which practically means that the gamma ray is going to be more powerful than a radio wave. That's why a gamma ray can cause cancer if it's not used correctly, and a radio wave cannot cause cancer reasonably. So, now we know all of these. We need to know further about the visible light. Visible light is a very important one, and let's examine that further. Okay, so have you ever thought of colors, right? Those are only the colors that we see. There are no more colors, and okay. Visible light. Visible light encompasses all of the colors a human eye can perceive. No more, no less. Human's eyes can only perceive to that amount of area. So let's go through all of our colors. So we start with red, orange, yellow, green, blue, and indigo, and violet. Red, orange, yellow, green, blue, indigo, and violet. And if we write them down in an acronym form, okay, so these are all of the colors a human eye can perceive. And what is interesting also is that they are in a spectrum. So I believe that the wavelength it goes like this. It starts at this end, which is about 380 nanometers, and it over here it ends at about 750 nanometers, which is this thing. Yeah. So I assume this is the rough color spectrum. Okay. So this is it for colors and the electromagnetic spectrum. Hello. After we have discussed waves and the electromagnetic spectrum and transverse waves and electromagnetic waves, we're going to discuss refraction through different medias. Okay, so what is refraction? Refraction is the phenomenon you see when light passes from a medium to another medium, which both have varying densities. And as you can see, when refraction is happening, light gets redirected. This is due to a change of speed. Let's say light travels from a medium with higher density to a medium to a lower density, such as glass to air. What happens is that light, once refracted, speeds up, so it bends away from the normal. And in that case, there's also a new definition for that scenario, and it's refraction is a phenomenon you see only when from a incidence angle of 0 degrees to the critical angle, and I will explain that later. And in a medium, when you're traveling from a lower density medium to a higher density medium, such as air to glass, refraction does not entail a critical angle. And once light is traveling from a medium of lower density to a medium higher density, the light actually slows down and bends towards the normal. So this is very cool, and but you might not understand anything that was said right now. So let's start at the beginning. So what's the speed of light in the vacuum? It's as far as I remember, let's say speed of light is s equals to 10 s equals to 3 times 10 to the power of 8, and the unit is meters a second. So this is the speed of light in a vacuum, and it is actually extremely fast. Yeah, and let's start by illustrating this. Let's start by illustrating refraction in a actual shape, and this shape is going to be the rectangular prism. We have the rectangle over here. It's not that well drawn. Okay, so firstly, you might be wondering, what is the normal? It's basically the line to the surface of a shape that creates. Okay, so you might be wondering, what is a normal? So the normal is basically a line that's perpendicular to the other line. So let's say we have this this side of the rectangular prism. The normal would form a 90-degree angle on both sides over here. So that's something to keep in mind, even though, like, if you create a right angle in one side, it's going to be that on the other side if it's a straight line. Okay, so let's start with light. So we extend the normal upwards and have, let's say, we have a light ray that's going to be traveling from over here, this degree, and it's going to refract. Okay, so now you might be wondering, let's just extend this out. Okay, now you might be wondering, what is this? What is this? Okay, let's say this is glass. This medium is glass. Glass. And this medium is air. So the light is traveling through the air into the glass. And now we also continue labeling. Okay, so I'm back. So what is this thing? You see the light? That's the incidence ray. So incidence ray, it's the light that is traveling, is the first light ray before any refraction. This, however, here is the refracted ray because it's refracted. Okay, so now we have the incidence ray and the refracted ray, and you can see as the light travels, it starts at the incidence ray, and then once it hits the glass, it refracts. And in this case, because glass has a higher density than air, light slows down as it's passing in. And now we need to know some other terminology, such as what is the refracted angle and the incidence angle. Okay, so basically, let's start with the refracted angle. No, the incidence angle. So this is the incidence angle. Let's just say over here. As you notice, I am measuring to this towards the normal. Uh, so we have the normal basically, and so in this case, the incidence angle is the angle formed by the incidence rate and the normal. Now let's continue to the refracted angle. So the over here, the refracted angle in this case is the angle formed by the refracted ray over here, which is mentioned too, and the normal. So there we have the shape with the light going from the air into the glass and now back into the air. And assuming it's gonna continue its normal path, it's going to go like this. Yeah, so this is simply reflection, okay? So now let's continue on to describe, yeah, the critical angle. Now that you understand what I mean by the normal and the higher density and the lower density and the light traveling through the mediums, let's go and describe what critical angle is. So let's just get a rectangular prism back again. Okay, so now we have there this thing, and then we're going to make the normal. And yeah, I mean, maybe make it extend all the way to the bottom. So we have the normal, and when light travels through the medium over here, assume this is a straight line. Yeah, this was not really that straight, but let's just do it again. You can see that the light refracts once it refracts into the air from the, let's say, glass. It's bending away from the normal. It's so if let's say we continue, we have another incidence angle over here. You will notice that the angle seems to be moving further away from the normal. The ray moves seems to be moving away from the normal again, and the thing is that once we reach one angle, which is the critical angle, let's say it's over here, and draw it up here, you'll notice that the refracted ray will travel along the rectangular prism. So at that point, the light is exactly traveling along, and any further degree is going to cause total internal reflection. So total internal reflection is, let's say, this angle is over here, then the refracted angle is over here. So it goes there and then gets into the shape. So once you as you notice, the light goes from an incidence angle, and then once it refracts, it actually never refracts. It only reflects. So that's the critical angle, and you need to be mindful of this because if let's say we have another the previous diagram over here. Assuming we have the previous diagram here, if we had a refracted angle that was bigger than the critical angle, there would total internal reflection would happen, and there would be no refraction anymore. Let's move on to Snell's law. So, Snell's law was a law that can also be called as the law of refraction. This is because it can describe refracted angle and refraction in a shape. So it's the sine of the theta. I think it's this thing. Let me check. Yeah. Equals. Okay, so you might be wondering what these things mean. Firstly, what does this mean? N1. N1 means the refractive index of the first medium. N2 means the refractive index of the second medium. So let's write it down. Let's just say refractive index. Okay, so this is the refractive index of the first medium, and this is the refractive index of the second medium. And then this, you might be wondering what theta is. So theta in this case means the refracted angle, which we previously explained. So okay, so as you probably have understood by now, the one means the first medium, and the two means the second medium. So you might be wondering, how can Snell's law possibly be useful? So let's remove these stuff over here, and let me explain. So firstly, let's imagine a new rectangular prism, right? And we have the normal line, and we have this. Okay, so these are the important things. So now we have medium one, which, so you might be wondering, well, how does this thing work? So firstly, let's think of any algebra. Usually, if there's only one unknown and everything else is known, it's very simple to answer. Same as here. If we, for example, know the refractive index of the first medium, let's say this thing is air again. The refractive index of the air is about 1. I'm pretty sure 1.0003. And let's say you also know the angle of incidence. And now, let's say we know these stuff. And refractive index. So, we on the other side, we also know the refracted angle. So we know what angle this is. So let's do some maths and find it out. How can we rearrange this formula to make it useful? So n1 sine theta 1 equals to n2 sine theta of 2. So simply, if you want to do something in maths, you have to do it by on both sides. So in this scenario, we don't know what this is. We do not know what the refractive index of the second medium is. So what you do here is that you isolate this by dividing this side by a sine of the refracted angle on the second medium. So it basically becomes n1 sine theta 1 divided by sine theta 2 equals to n2. So now, once you use this formula, you can find out what the refractive index of the second medium is, and this can be done in other ways to find other unknowns. And this is very useful because the Snell's law itself can describe both. This is useful because with the Snell's law, you can find out 4 different things. If you have 3 pieces of information, you can find the angle of incidence, you can find a refractive index of the first medium, you can find the angle of refraction and the refractive index of the second medium. Let me check if that's it. Moving on to a triangle, we're going to discuss how light refracts through a triangular prism. Okay, so let's start by illustrating a triangle. And this, let's label this as a triangular prism. Okay, so let's begin. So first we need to have a light ray which is entering it, which could be at this angle. And now we call this the incidence ray. No, it's called the incidence ray. And we also have to make the normal now. So it's going to be perpendicular to this side. So we can okay. Now that we have the normal, let's label this the normal. And let's say that the medium is made of glass, and this is air. Okay, so since the refractive index of glass is bigger than the refractive index of air, it means that it's moving into a denser medium, and if it's moving into a denser medium, it slows down and bends towards the normal. So as we can see, the refracted ray bends towards the normal. Okay, so let's call this the refracted ray. Okay, so this is called the refracted ray. And after that, we also have the emergent ray, so the ray which is leaving. Okay, so now we can form some angles. Firstly, we can form the angle of incidence. So this is the angle of incidence. It's the angle formed by the incidence ray and the normal. Then we have the angle of refraction. However, this one is not that important. And we also have the angle of emergence, but this is also not important. And we can also form this thing if we continue the emergent the incidence ray as if there was no medium. Let's continue this up. We get this thing. We have the angle of deviation. So angle deviation is the angle formed by what would have been the incidence ray if there was no medium, and the emergent ray if it was extended. Okay, so this is simply a very simplified version of how light moves and refracts through a triangular prism. And of course, there's still a critical angle in a triangle. It is 48.6 degrees, and a total internal reflection still happened. And it's when the refracted angle is bigger than 48 point. No, it's when the angle over here to the normal is bigger than. Yeah, it also happens in this in the triangular prism. Okay, let's move on to light dispersion. So let's get a triangular prism back. So, what is light dispersion? So, imagine light, the white light. White light, it can be split to different colored light, which is red, orange, yellow, green, blue, indigo, and violet. Okay, so these colors have their different wavelengths and different wavelengths to each other, which with this side having longer wavelengths and this side having shorter wavelengths, and thus these wavelengths impact their refractive index in this medium, in the medium, because the wavelength correlates with the speed of the wave. So we can imagine this. We have white light which is entering, and once it disperses, where the red is at the top and the blue over here is going there. Yeah, and like imagine this as the light passing through. So, what do we notice? We do notice that it seems that the shorter the wavelength, the more they bend towards the medium, and the longer the wavelength, the the less they bend towards the medium. They actually do not bend toward the medium. The less they bend towards the medium. So this is simply how light dispersion works, and that's it for this. Moving on, we're going to discuss lenses. So lenses, what are lenses? Where do you see lenses? Lenses are the stuff you can find in cameras, telescopes, and microscopes, and they help focus light. So there are two types of lenses we're going to discuss. There's the convex and there's the concave. Technically, these are called biconvex and biconcave because it's on both sides. And let's label them. Convex, concave. A simple way to remember both of them is imagining them with their physical appearance. So the concave, you can notice there's an inner bulge on both sides, and this resembles a cave, as in because caves you wander inside, and convex, just remember that it's not concave, or you can remember that it looks like a water drop that is symmetrical top to bottom, and both of these focus light differently. And as you notice here in the concave, the middle is thinner than the top and the bottom, and in the convex, the middle is wider than the top and the bottom, forming these shapes. So let's see how light manages to how they manage uh, how light travels through the convex and the concave lens. So let's start with the convex. This illustration, I need to get it correct, so wait a little bit. Okay, this is not the best illustration, but it's decent. So what happens if light moves straight ahead of it in the middle? It just moves past it. And if it moves into the over here, the light is being refracted like this, and they converge in to one point. Okay, so you see, once the light travels through the convex lens, it converges in one point, and then it spreads out. So, what can this do? Imagine this as it can focus light. Yeah. So, as if the light is focused, you can, for example, use it for microscopes, because microscopes focuses this light, so you can practically zoom in. Now let's move on to the concave. As you can see, that once the light is for the concave lens, you can see if the light is hitting directly at it, it moves. It doesn't change. But if the light, for example, moves at this angle, you can notice that it's slightly diverging. What's diverging? It's the opposite of converging. So it's moving away. And you can notice this. And let's say you go here, then it's like diverging even further. So this is kind of exaggerated for dramatic effect, but the main thing you need to know is that the concave lens can diverge light. And let's think of something that it can be used for. Let's imagine you were taking a picture of your camera. So you might sometimes notice the times 0.6 feature, and you wonder how does it work. It's firstly, why would you use it? You want to fit more into the frame, and because the light is diverging, you can see more with the light, which previously showed only this amount, which means that even though it might be very confusing, the concave lens in your camera can make it so that you zoom outwards.